Chapter 2.2 is about Kirchhoff's law. And before introducing Kirchhoff's law, I would like to introduce the definition of nodes, branches, and loops. The branch represents a single element. From the first figure, we can see that each element is represented by a branch. So the voltage source, the resistor, and also the current source, they are one branch. And the node is the point of a connection between two or more branches. So here we can see that the voltage source and the resistor is connected at point A. So A is a node. And we also see that the 5 ohm resistor, the 2 ohm resistor, 3 ohm resistor, and the 2 ampere current source all connected to B. And because there are 3 points here, but there is no element between these among these 3 nodes, so this is only one node, not 3 nodes. Yeah, if the short circuit connects 2 nodes and the 2 nodes constitute a single node. The same thing for node C, because there is no element there, so it is one node. The other example is that we can see in the second figure, the node A, it is connecting the 10-volt voltage source and the 5 ohm resistor. For the node B, it is connected with 3 resistors and 1 current source. And for node C, it is connected with 2 resistors and a voltage source and a current source. The loop is any closed path in the circuit in which no node is encountered more than once. Let's take a look at the first figure. For example, we can draw the loop here. So a loop can consist of the 5 ohm resistor, the 2 ohm resistor, and consists of the 10-volt voltage source. So this is one loop. We can have another loop, for example here, right? And the other loop here, this is another loop. And also we can have a bigger loop, for example, which consists of the 5 ohm resistor, the 3 ohm resistor, and consists of the voltage source. This is also a loop. So there are many loops in the circuit. For the second figure, we can plot the loop, first loop, second, third, and we can also have a larger loop. For example, this is also a loop, or the whole loop. These are all loops. So there are many loops. And next, let's talk about the series circuit. So the 2 or more elements are connected in series when they belong to the same branch. And so in general, the circuit elements are in series when they are sequentially connected end to end and only share binary mode among them. So it's obvious that. But the property of series circuit is that elements that are in series carry the same current. This is a property of the series circuit. For the parallel circuit, the 2 or more circuit elements are in parallel if they are connected between the 2 true nodes. And the property is that the parallel elements have the same voltage. This is a parallel circuit. Okay, now let's first talk about the Kirchhoff's current law. The Kirchhoff's current law states that the algebraic sum of currents entering a node or a closed boundary is 0. Let's take a look at this figure. There are 5 currents, I1, I2, I3, I4, and I5. Some of them are entering the node and some of them are leaving the node. So we can denote the current entering the node as positive and denote the current leaving the node as negative. So we can get this KCL equation. And also we can write down another equation. That is, first we write down the current entering the node, that is I1 and I3 and I4. That's the current entering the node, and which equals the current flowing out of the node, that is I2 and I5. So the KCL has two forms. I prefer the second one, is that we write down the sum of the current entering the node, which equals the current leaving the node. So remember this. This is KCL. Let's take a look at an example. Write down the KCL for every node and assuming the current leaving the node are positive. So let's take a look, for example, at node 1. Node 1. There are 3 currents, I1, I2, and I3, right? So, oops. So that is the I1 equals I2 plus I3. This is for the first node. The second node, this is for the first one. The second one, we also have 3 current. We can say that the current leaving the node is I1 plus I6. The current entering the node is I4. So that is I1 plus I6 equals I4. The third one, it has 3 current. The entering current is I2 and I5. So I2 plus I5 equals the current flowing out of the node, that is I4 plus I7. For the fourth node, 3 currents. I3 and I8 is flowing into the node. I5 is flowing out of the node. So I5 equals I3 plus I8. And for the node 5, I7 is entering the node and also I6. So which equals the current flowing out of the node equals I8. So these are the other KCL equations for this circuit. And another example is that find the unknown currents in the network. Let's take a look. Let's start from maybe I1 for node 1. For node 1, I1 is entering the node and 60 and 20 are out of the node. So equals, which is 80. So we can easily calculate I1. For another one is, we can see for node 4, I5 is leaving node 4 and 20 and 30 are entering the node 4. So I5 equals 20 plus 30. So that's 50 milliampere. So we know I5, we know I1, right? We can, how about calculate I4 for node 3? I4 is leaving the node 3, so I4, and this 40 is also leaving. The leaving equals entering, so that is 60 plus I5. I5 is 50, so we can get I4 equals 70 milliampere. So finally, we calculate I6 for node 2. I6 is leaving, so and I4 is entering. I4 is 70, right? And I1 plus I6. We know I1 is 80, right? So I6 equals -10. So we find all the unknown currents in the network. The next is that the KCL also applies to a closed boundary. So that is the total current entering the closed surface is equal to the total current leaving the surface. So this is a closed boundary. So we can see here, we can the leaving is I1 leaving. This is I2, I3, and this is I4, I5, right? So we can see which one is leaving. The leaving the boundary is I1 plus I5 plus I4, and the current entering the boundary is I2, I3, right? So we can generalize the KCL, not only apply to a node, but apply to a closed boundary. We will have an example. So here we have a boundary. We do not care the current inside the boundary, but we only care about the current flowing into and flowing out of the boundary. So we can see that we have I6, I3, and I7, but we do not have the current entering the boundary. So their sum should I6 plus I3 plus I7 should equal 0. This is KCL applied to a boundary. A simple application of KCL is combining current sources in parallel. We can see there are 3 current sources in parallel, and IT is their total current. So we can apply KCL at this node. We know that IT equals I1 minus I2 plus I3. That's the total current. So we simplify the circuit. The circuit which has 3 current sources can be simplified using a circuit which has only 1 current source. Okay, next we talk about the KVL, Kirchhoff voltage law. It states that the algebraic sum of all voltages around a closed path or closed loop is 0. So from this circuit, we can see that this, and also let's define the positive and the negative voltage. So when we move from the plus to minus sign, we add VA, and we move from the minus sign to plus sign, we subtract VA. So let's take a look. In this loop, first we encounter V2, so it's plus sign to minus sign. So this is we have V2, and also V3 plus to minus, so plus V3, and V4 it is opposite direction, right? From the minus sign to plus sign, so that is minus V4. And for V5, plus to minus, so plus V5. V1, minus to plus, so that is minus V1 equals 0. So this is the KVL equation for this circuit. So the one application of the KVL is to simplify the series connected voltage source. For example, the three voltage sources are connected in series and their output voltage is denoted by VAB. So we can write down the equation. So we choose this loop. Choose this loop. So first we encounter V1. So it's from plus to minus. So that is V1. And then V2, also plus to minus. But V3 is the minus to plus, minus V3. And VAB is minus to plus. So minus VAB equals 0. So that we can get VAB equals V1 plus V2 minus V3. So we use one voltage source, that is Vs equals V1 plus V2 minus V3, to represent the three voltage sources which are in series. And KVL, let's take a look at the KVL. We know VR1 equals 18 and VR2 equals 12. We need to calculate VR3. Choose a loop and write down KVL. So VR1 minus 5 plus VR2 minus 15 plus VR3 minus 30 equals 0, right? So VR1 equals 18 minus 5 plus 12 minus 15 plus VR3 minus 30 equals 0. So this becomes 13, so 25, 10, this becomes 20. So VR3 equals 20 volt according to KVL. So this is one application of KVL. And another example is to write the KVL for this circuit. We can see that there are three loops. The first loop, loop 1, the second loop, loop 2, and we can have a big loop, the third loop. So we can write down three KVL equations. For example, for loop 1, we have the VR1 plus VR4 minus 16 minus 24 equals 0. For loop 2, we can start from B. VR1 plus VR3 plus 8 plus 16 minus VR4 equals 0. And for the big loop, we have a big loop 3. So for loop 3, let's start from point A. So VR1 plus VR2 plus VR3 plus 8 and minus 24 equals 0. So these are the KVL for this circuit. And also when we apply KVL, 2 points, 2 nodes does not need to be physically connected by wire. In this example, the node A and the node E are not connected with each other, but we can also apply KVL to calculate its voltage, that is a VAE. Let's take a look. So VAE is plus or minus, right? So we choose this loop. So that is VAE plus 10 minus 24 equals 0. So VAE equals 14 volt. And how about VEC? VEC. So VEC, we choose this loop. So VEC plus 4 plus 6 equals 0. So VEC equals negative 10 volt. So in your homework, you will have similar problems. Okay, now we have some interesting implications of KVL and KCL. So that a series connection of two different current sources is impossible. Why? Because in series, the current I1 must equal to I2, right? But for different current sources, their current are different, so it does not satisfy the requirement. And for the parallel connection of two different voltage sources is impossible, because when they are in parallel, the V1 must equal to V2. It's not possible that V1 is not equal to V2. And also that a current source supplying zero current is equivalent to an open circuit. So when the current is zero, it means no current can flow through the wire. So we use an open circuit to represent when the current source is supplying zero current. And a voltage source supplying a zero voltage is equivalent to a short circuit. The zero voltage on the voltage source means that there is no voltage drop between the two terminals. So we use a short circuit to represent it.